Okay. So these are definitely ones where you're just going to have to do a bunch to say, hey, when do I use this identity? When do I use this identity? Look at M and odd, M and N equal to odd numbers or even numbers. Or there's a lot of algebra, and you can make some easy mistakes in there. So it really is just it is complicated, and you just got to be real careful. We'll do as many as we can. So
also,
go ahead.
also I was looking at it. So as long as if one of them is even, you have to separate it out to where it can become odd or be operated as an odd value. You have to do that.
Right. Yeah. If they're both even, you have to use the double angle formulas to condense it down into cases where either you can just straight up do it, or it'll simplify it down where probably, then one of them will be odd, or maybe both of them will be odd. And then you may even have to go a second step on top of that to go from there. So they can get pretty long. Yeah. All right. So that was the first class. So maybe we'll do some more if we have time. This is the second one where it's not powers, it is multiples on the inside. And so you get sine 5x, cosine 2x. And I know that these might look bad, and you're like, am I ever going to use these? And the answer is, if you're an electrical engineer, definitely. This is on Fourier analysis. You're going to see sines and cosines on your oscilloscope all the time. I think in ME and CE, it might be a little bit later. Certainly, if you go to grad school, I've had people come back from grad school and be like, why didn't I pay attention? Although that's a few years off or some. So, but it is related to Fourier analysis, heat transfer, vibrations, and anything that's like that is oscillatory in nature. It'll definitely be sines and cosines. So we have ones that look like this. So it's sine of 5x times cosine of 2x. In this case, just going back to the book in the back, you have these formulas, which are called the product to sum formulas. So I think they're on like appendix page 18. They're near the end, and so these are the formulas that we're going to use. If you have a sine and a sine, you'll use the first one. If you have a cosine and a cosine, you'll have the second one. And what we're going to want is this last one down here because we have sine and cosine. So what it says, if you have that, you can recombine them into a sine that's the two numbers added and a sine where the two numbers are subtracted. And then you put those together and you're basically averaging them. So here, let me sort of rewrite that off to the side. Again, it's the product to sum identity. And there's three of them, but they're all pretty similar. But the one for sine of something, cosine of something, we're going to, I guess I can just get rid of the integral for just a second here. Before we even do the integral, just the identity is, I'm going to put something in here and here. The book uses x and y. We already have x's. I don't want it to be confusing. So I want to put something else here. But, well, maybe this is going to be confusing too. I don't know. But if I do sine of A, cosine of B, I can replace that with the sine of A plus B plus the sine of A minus B all over 2. So that's that product to sum identity that I just showed you in the book. They had the half in front, but I'm writing it just because I was about to run out of space. So that means that this interior part, I could use that.
Wait, that's sine of A plus B twice?
That's a minus.
Okay.
A plus B in the first one, A minus B. It's easier just to like show again in the thing. It's you add them together in one sign and then you subtract them in the second sign. And again, they put the half out front. I just put the half as division. They're the same. So I'm going to have, and maybe I'll just do it this way, 1/2 and it will be the sine of the two things together added together. So that'll be 7x. And then I'll have the sine of the two things subtracted, which will be 3x. So add the 5 and the 2x to get 7x, or subtract them to get 3. And so that's the identity that you use in order to simplify the integral stage 1. Now you still have to do it, but at least that's the simplification step. So let's see, I can write this as a half sine of 7x plus sine of 3x if you want to throw one extra step in there to pull the half out. And now each of those are technically little u substitutions, but they're sort of small enough that I think we don't have to go through the whole step. And you want to let u equal 7x, so there's going to be a 7 in there somewhere. I know it's minus cosine because the integral of sine is minus cosine. So I have minus cosine of 7x, and to balance out that 7, you have to divide by 7 when you're doing integration. And again, it's a mini u substitution, but you do this enough over and over and over, you start to see patterns. So that's one of them. So that's the first one. And then that half is still going to be on the second one, which looks very similar. It's minus the cosine of 3x divided by 3. And so that integration there. So in the end, you can, I guess, leave it like that. If you wanted to clean it up a little bit, you could write it with, combine the denominators, I guess. So minus 1/14 cosine of 7x and minus 1/6 cosine of 3x. Like that.
When you have
go ahead.
When you have something in the cosine or sine, the denominator looks like it's just a derivative of whatever is inside the cosine or sine.
That's what it is. That's exactly right. Yeah. And why does that happen? You know, if we just came over here to the side and said, if we did the sine of a number, so I don't know, do we need another letter for this? We haven't done A, just little a, like this. Then, technically, you know, when you do the derivative, maybe just do 2 steps here. If I do the sine of ax derivative, the answer is, well, it should be the cosine of ax, but then the chain rule kicks in, and I have to multiply by the derivative of the inside, which is a. So cosine of ax multiplied by a. This one, if I did a u substitution, u equals ax, then I'll get the integral of sine of u. It catches the dx here. Du is a dx, so that means that we're running out of room. Dx is du divided by a. So when I put in dx, I have to put du, but then I have to divide it by a. And so then when I integrate this up, I'll get 1 over a negative cosine of u. And then when I replace, I'll get negative cosine of ax over a. So just what Travis said is that a just ends up being the denominator. And that works if it's a multiple. And the same thing is going to work here. Since it's 3, I end up getting a 3. If it's 9, I get a 9. That only works if it's like a multiple of x, nothing else.
What about if would it also work if it's like x squared?
No.
No?
Yeah, that doesn't work. Constant multiples are nice because you can multiply them like anywhere you want. If you did x squared and you tried this trick, the derivative would be 2x, and there's no x to balance it out. I could always multiply by 2 or divide by 2, but you can't just like randomly multiply or divide by x. And you can see that by checking your answer, it would be thrown all off. So that's a pretty special one. But if it's just sine of a number x, it ends up having that number in both places. But yeah, I mean, it's a pattern that comes out when you start doing this stuff. So I don't know, let's try that again. What happens if it's not sine and cosine, but 2 cosines? So same example where it's the integral of cosine of 5x and cosine of 2x. Well, we go back to the book, and we want product to sum. It's not the first one because that's two signs. It's not the last one because that's the one we did. It's the middle one. So if we want to do this, it's 1/2 two cosines, one where the inside is the subtraction of the two, and the other where it's the addition of the two. It looks really similar to the sine. It is. We're basically just changing sines and cosines around. So let me just recopy that up here. The identity, if you said cosine of A, cosine of B, it turns out to be cosine of A minus B plus cosine of A plus B, and either multiply by 1/2 or divide by 2, whichever one ends up to be easier for you. So if I replace this entire inside using that, A and B subtracted will be 5 minus 2, so 3x. A plus B will be 5 plus 2, and that'll be 7x. So the first one will be the cosine of 3x. The second one will be the cosine of 7x. And they're added, and then divide by 2, but just like in the last one. Dividing by 2 is the same as multiplying by 1/2, and I'm going to multiply by 5.
So A and B have to be in their own way constant multiples. They can't be something like they can't be an exponential function at all or anything like that.
These are super specialized ones. Just cosine of a number times x, cosine of a number times x, or cosine of a number and sine of a number, or sine of a number and sine of a number. So it really is like very specialized to only those 3 specific cases.
It can so it can be something like 1/x or x squared, right?
No.
Okay.
Yeah, I mean these here's the thing. In Calc 1, if you want to do a derivative, you only try like 3 things: power rule, or product rule, quotient rule, or chain rule, and that works like for everything. In integrals, there are like 1,000 different rules for these sorts of things, and it is never like one might be looks very similar, but it'll throw everything off. So there's a book in the library that's like an integral table book, which is about 1,100 pages long. And it's just got integral after integral after integral after integral. What about this? What about this? What about this? What about this? And little changes can cause massive changes in your answer. So yeah, the point is this is for very specific type. You can't have any crazy functions in it. So if we try and do this integral, again, the integral of cosine is sine. And I know it's 3x, but we've just sort of seen that if you divide by 3, it balances it out. That does not work for x squared or 1/x or e or anything. It's just it's a multiple of x. This will work. And the same thing here. Sine of 7x over sine. So the key here is this product of trig identities to the sum of trig, or product of trig functions to the sum of trig functions identity. And so you just have to recognize that that's the case.
So does when you're using cosine or sine, does that affect whether it's A minus B or A plus B first?
Yeah, it's well, I mean, right. So you look at these last two. Because they're added, I could have switched the position. So maybe these last two really should have just been cosine of the plus cosine of the minus. It doesn't matter how you do the last two. You see that? I can take and reverse this. The first one does make a difference because there's a minus in there. So you do have to do the cosine of the subtraction and the cosine of the addition, and you have to subtract in the right order.
You cut out like right after I asked the question. I didn't hear any of what you said.
Okay, sorry. Yeah. So I mean, look at what we have here. One of these guys is the cosine of 7x, and the other is the cosine of 3x. And it doesn't matter if I did the cosine of 7x first or the cosine of 3x first. I'd still get the same answer. I just might have these written in the opposite order. But it's a plus, so that doesn't matter. The only thing that does, so that doesn't matter in the cosine cosine or the sine cosine. It does matter on the first one, because if I subtract, I'll get the 3x here, and I'll get the 7x here. And it does matter because of that right there, that minus. If I went in the wrong order, I'd get negative the answer. So that's the only one that really matters, is you have to do the subtraction first, and then the addition second, and then subtract. Right? Just watch for the minuses. Okay, so that's the second class. And I know I've only done a couple of each type, but don't worry, in the homework you'll have plenty of practice on these things. The last one, which is like, oh, this is a lot harder, maybe a lot harder, is we have tangents and secants, which we're not always so used to. And not only that, but it's tangent to a power and secant to a power. So I think we're going to have to spend a little more time on these to get them down. So let's see. I have to recall our facts here. That if you take the derivative of tangent, you get not secant, but you get secant squared. So that square is going to cause a little bit more difficult than the previous one. That's that. The derivative of secant, now you might have to go way back in your brain, or who knows, maybe you didn't do too many of these. It's actually two pieces. It's got the tangent times the secant. So both of those together form the derivative. So now you're like, crap, I got secant squared, and I've got tangent secant, and I've got tangent of the power and secant of the power. And how do I like suss all this stuff out? So we'll try. And then the main identity between these, instead of sine squared plus cosine squared is 1, it's 1 plus tangent squared is equal to secant squared. So all of these things, combined with U substitutions, combined with M and N being even and odd, there's actually like 4 different cases we're going to have to deal with, and it's just going to take a lot of practice. So this part does not come as easy. So I hope through some examples we can see what's going on, but really it's just going to take quite a lot of practice. So here we go. So here's the first one. Let's try tangent cubed and secant cubed. Let's plug it. Okay. So, how do I deal with this? Well, I could possibly use this identity up here. Maybe I can't quite do a direct U substitution, because if I tried tangent, I'd get secant squared, and that doesn't quite work. I have a cube. So if I had a square there, I'd be in great shape, and I could just use a regular substitution. But I don't. And I also have, I don't know, there's a lot of pieces in here. So let's try this identity up here, and let's replace, or here's what I'm going to do. I'm going to write this as tangent, and then take 2 of the tangents off and write it as tangent squared. How do I know to do this? Practice, lots of practice, pattern recognition.
Whenever we see any kind of odd, just break it up between, pretty much most of the time we see tangents, sines, or cosines that are odd. Just break it up into smaller parts where there's at least one majority of even ones, and then just kind of solve from there.
That could be right. That could be right. I don't know. Am I still good? My thing said I'm a little unstable. So let me point in if I drop out. Not only because I want to use the identity on that one there, but I also want to do this. So I want to break the secant up as well. So tangent and tangent squared, and secant squared. what? Why do I want to do that? Well, I want to use the identity on this up here, and then this tangent and this secant together are right there, tangent and secant together. So I'm going to just rewrite a little bit. The tangent and the secant here become tangent, secant. That looks pretty good. That's part of my answers up here. The starred thing, if I solve this top one by tangent, then I can move this one to the other side, and that will be secant squared minus 1. So that's the star part. And then the secant, I just leave by itself, secant squared. So this is definitely where the pattern recognition comes in, is I've got secant, and I've got the derivative of secant right on the front. So this is like advanced U substitution here, is that U equals secant, and that's going to go in two places. And I use the derivative of secant, which is tangent times secant dx, to be the rest. So everything here that's kind of underlined goes with du, and the rest goes with u. So it does simplify down really nicely. The secant squared, I just get u squared minus 1 for that one. Lots of arrows going on right here. Plug it into the second one, I get u squared. So secant squared minus 1, secant, so it becomes u squared minus 1 and u squared. And then tangent, secant, dx, all together is du. And so there's your substitution. And it looks kind of yucky, but breaking it up, like Kyle said, but reorganizing it in a way that makes sense. I don't know. It takes some practice. Keep saying that overnight. So now I can actually work this out. Distribute this through. I get u to the 4th minus u squared. This is an easy integral. I get 1/5 u to the 5th minus 1/3 u to the 3rd. And then, so let's squeeze it in. I replace those u's here. So I replace, and I'll get 1/5 secant to the 5th minus 1/3 secant cubed plus c. Now I'm done with that the plus c on it. Oof. A lot going on in there for sure. So identities, using the correct U substitution, doing the correct algebra, and then getting down to here. And you can check. Take the derivative of your answer, you'll get right back up to the beginning, tan cubed secant cubed. So there's that. Let's just keep going. We'll do some more examples, and maybe some of this stuff will start to click a little bit. So tangent is a 4, just tangent by itself. Okay, so now it's not odd anymore, but actually I still want to write it as tangent squared times tangent squared. If you're not sure what to do, just start breaking it up and start to see if any of the pieces make any sense to you. So tangent to the 4th means a square times a square. Okay, this one I'm going to use the trig identity again. The tangent squared is equal to secant squared minus 1. So that's the identity that I had on the previous slide. I just moved the minus 1 over. So I'll get tangent squared. Again, if I freeze up, let me know. My thing is giving me issues here. So I just replaced that one right there. Now, why is that helpful? Well, I think two more. You need to break it up just a little bit. So distribute, and I'll get tangent squared secant squared, and I'll get minus tangent squared dx. Now, just maybe it's a little easier to do these separately, so we're going to try and do them separately. I think I'll try to put it underneath. So I'm going to break this up into the integral of tangent squared secant squared minus the integral of tangent to dx. And now I've taken my one problem and I've turned it into two. Yay! Let's take the math problems and have them multiply here. And now I have two problems to solve instead of just one. So we have to solve both of these, and they may not be done in the same way. In fact, they are not done in the same way. So I'm going to have to do one method on the first one, and I'm going to have to do one method on the second one, and I'm going to have to add them together. So I think I can fit it in. If not, I can use try and expand it. Put it in a little better here. So this first one, I want to use a U substitution, U equals tangent. How do I know that? Well, I recognize I've got tangent and I've got secant squared, and that is the derivative. So this part right here should be du, and in fact it is. The derivative of tangent is secant squared. And so that lines up perfectly. Everything lines up perfectly in the second one, like we're in the first integral here. This is u squared, and the rest is du. This is sort of as easy as you're going to get. Again, yeah, that's u squared, and the rest is du. And now
so I was wondering, could you take tangent squared and just do the same thing, where you just make a secant squared minus 1, and then just kind of
here?
Yeah, I was wondering that if there's an option or no.
You can try it if you change this and then you distribute back through, you'll get secant to the fourth. And you can do that, although you're making it harder. Let's say that. That's one. I mean, and it's hard to know why, right? You plug in secant, you multiply it out. You're like, okay, I got secant squared. That's not too bad. But then I have secant to the fourth, and none of my substitutions work anymore. So that's probably just a sort of a hint that you've overcomplicated it or made it even. Yeah, you just really made it harder. We're going the wrong direction. But try it. I mean, try all those things and see what works for you. And trust me, this is going to take a lot of scrap paper. So integral. Okay, so finish this one off. So 1/3 u cubed, and then I just replace. And I get 1/3 tangent. Okay. Tangent x cubed. So that's the answer to the first one. Maybe I can just go ahead and write it over here. Tangent cubed times a third. So that's that's the first integral. How about the second one? Well, I actually have to use my identity again. That secant squared minus 1 is equal to tangent squared. So I have to use the identity again. How do you know that? Practice. Recognition. I don't know what the integral of tangent squared is. I know secant squared is tangent, the integral of secant squared. And by doing this identity here, and that's exactly what I get. This secant squared integrates to be tangent. I know I'm going to tangent x. And then the 1 is, now that's easy, that integrates up to just x. So if I take that answer and subtract it off, then I'll get tangent x minus 1, or minus x. That is the answer to the original problem. So it's weird. I mean, you start off with the tangent to the fourth, but your answer is only tangent cubed and tangent on x. So it's like, shouldn't the power go up? I mean, this is where it starts to get a little mysterious and maybe some of your intuition kind of falls apart. But, again, I think it's just a lot of practice. Maybe we'll try one more of those if I can find a good one. I forgot to do that. I don't know. Here's one that I didn't. This is terrible. This is definitely one that I think you should just. You could look it up in a table, or I should have done this before because it's actually a substitution question. So I think this one was actually in 6.1. We didn't have a chance to get it. So this is not really from this section, but it could come up. It could come up as a part of one of your problems. So if we want to do this problem, this is super difficult. This is like, there's no way you would figure this out. So I think I'll just have to apologize in advance that it's just one that's tricky. So what you can do is you can do this. You can take any function you want and you can multiply the top and the bottom by exactly the same thing. And that will not change anything. If you multiply the top and the bottom by the same thing, you're multiplying by 1. So it's like multiplying and then canceling it right back out. And sometimes in math classes we do this in order to introduce some stuff that we're actually going to need. So this is, no, I'm going to try that again. This is definitely like black magic. Neuromancers. But anyway, if we multiply the top and the bottom by secant plus tangent, just trust me for a second. Then, and distribute this out. So 2 steps. Multiply the top and bottom by the same thing. Then the top will be secant squared plus secant x times tangent x. And then the bottom is secant plus tangent. And now here's why you want to do this. Is because the derivative of secant is secant tangent. And the derivative of tangent is secant squared. So I can rewrite this integral by this method here as secant squared plus secant tangent. Divided by secant plus tangent. And the reason why I want to do that is because then I can do u equals secant plus tangent. And that's in the denominator. du is exactly the top. It's secant squared plus secant tangent. dx. So this whole integral, it's super ugly, turns into something super nice, which is just 1 over u and du. Ta-da! Black magic. And we get down to this. And if we just finish it off, we get the natural log of u. And I don't have enough space, so skip down here to the bottom. I replace, and I will get with the integral of secant x dx. It's the natural log of u, where u is this crazy substitution. It's the natural log of the secant plus tangent and plus c. So, yeah, there it is. One of those that you see once and you're like, ah, that's terrible. And then you're like, screw it. I'm just going to go back to the book and let's see if that's an identity in here somewhere. Magically, lo and behold, it's number 13. So, come on. Right there in the middle, number 13. And you get one similarly for cosecant and tangent. I mean, all these weird ones here in the middle you need because they're individual integrals of trig functions, but they end up having natural logs in them because of this nasty trig that we did over here. So I'll apologize occasionally for math, and that's like one time I'll apologize. So that's no good. Yeah, so let me just break right there for right now and see if you guys have questions on read on the homework. So yeah, let's chat about the homework if you have any.
I really just have questions on tests. That's it.
Well, email me that stuff.
Okay.
So let's see. Today is July 1st, so the homework due is 6.2. That's all this integration by parts problems. We can talk about any of those, or if you're like, crap, we have homework due today. Well, you got a couple hours to knock that out. So if you want to stick around and talk about homework, you can. If you want to go work on homework, you now have the stuff we just did for tomorrow, and then the integration by parts. But this stuff will start piling up. So I'll tell you now, if you have questions about anything, please ask on substitution, basic integrals, coming up through integration by parts, trig integrals. The next stuff that we're going to do is something called partial fraction decomposition. So how do you deal with one polynomial divided by another? We're going to go into hyperbolic functions. It's just going to pile up. So get any questions you have answered or need answers to answered now, or at any time from here on out. So anyway, if you want to stick around, and if not, enjoy your day.
Thank you, sir.
I've got a really quick question about your like your turn-in time policy.
Yeah.
Yesterday, I remember you saying we could turn it in a little bit later, because we were working on it still.
Yeah, I mean, the key is to get these in. I grade them mostly on if you did them or tried them. So the grades usually are pretty good. The comments are important, that even if you get them like something written down, it doesn't necessarily mean it's right. So it's a balance between trying to let you explore, and then I put comments in there, and then coming back and revisiting it. And as far as deadlines go, now it's sort of set 1 o'clock just so you can have something to aim for, because that's the way it works, right? If I said midnight, people would be like, oh, I could start it at 10 p.m. So if I give a 1 o'clock, it's like, well, all right, I'll start at noon. So cadets love that. It's, you do it at the last minute kind of thing.
Right. I just thought I would ask because I started it.
Yeah.
And some of it I got a little bit stuck on, so I'm gonna work on it later. But I've got a thing that I have to do at 12:30, so I don't know if I'll finish it all.
Get it in. Just get it in, and maybe that's an exception for today. Try to aim for 1 o'clock most days. If it's a little bit late, I'm not going to freak out. If it's like a day late, then I might get that's a little sketchy. But
okay.
Trying to be flexible.
So preferably 1 o'clock, but at the very least the same day.
Yeah, that's a good summary.
Okay. Thank you, sir.
Okay.
So I have a question about number 13.
6.2?
Yes, sir.
Okay, 6.2. Say it again.
13.
13. Oh, yeah. Okay, this is one of the ugly ones. If you do look at the integral table, I think, where is it? Maybe it's not in the integral table. Huh. Well, that's not going to help us very much. So this is one where you have to do integration by parts twice, and then you have to do some algebra at the end in order to get it to work. We did one like this, I think, which was E and sine, and it's very similar to that. So here's what I mean. This is one where it doesn't matter where you put these two functions. So I think it's a little bit easier to put the U here and the v prime for cosine. So let's follow this through. So I know I need v, which is sine, and I know I need u prime, which is e to the 2x, but then you multiply by the chain rule, which is 2. So you got that part set up, then at least this answer is u times v, so that's e to the x sine x, e to the 2x sine x, and then minus the integral of the other two multiplied, or v, sorry, uv minus the integral of v u prime. So these two things multiply together. So I have a 2, an e, and a sine. So I can write it as 2 integral e and sine. And that's where you look at it and you're like, wait, that didn't help. Because I went sort of laterally from cosine to sine. It didn't get harder, didn't get easier.
It looks about the same.
But it turns out you need to do the integration by parts on this one again. And so if we try that again, same ordering, don't like screw up the ordering, where u goes first, but now v prime is sine. So we want to use the integration by parts on the second part using that ordering. So follow that through. Again, u prime will be 2e to the 2x. Here, v will be the integral of sine, which is negative cosine. And we apply that to this second one over here. So I'm trying to recopy here. So e to the 2x cosine x equal to, just recopying that term, so e to the 2x sine x. And then this last one, minus 2 is still a factor, and then that whole integral, I use all these pieces down here. So now it's the new u and v, so that's a minus, an e, and a cosine. So I have minus an e and a cosine. And then the formula has minus the integral of v and du prime. So it's these two guys, the v du. So I've got a minus from the formula. I've got a minus from this v. I've got a 2, so that'll be plus 2. And I've got an e, so put that in, and I've got cosine. So if you got all those parts in place, you'll notice that you started with an e and a cosine, and you ended up with an e and a cosine. So you're like, didn't I just like go in a circle? And it looks like it, but this is one of these weird ones that you didn't quite, because you ended up picking up a 2 twice, these multiples of 2. So if I distribute this out into each piece, I'll get this. I'll get e to the x squared cosine x dx equals e to the 2x sine. So that's, again, just recopying that. Then I distribute the 2 on the first one with a minus 2 and a minus, so that becomes plus 2 e to the 2x cosine. And then the minus 2 will multiply by this 2 will be minus 4 copies of the original function e to the 2x cosine. So it's like I started with a single copy of that integral. I ended up with some junk, these functions here in the middle, and then I took away 4 copies of the same answer that I wanted. So what I want to do is I want to combine these two things together. So I basically take this term and move it to the other side. The whole thing, which looks weird, but this is one of the few cases we do this. If I have 1 copy of the integral here, and I've got 4 copies of the integral here subtracted, when I move it over, I want to add 4 copies of the integral to this side. So I have 1 copy already, and I'm adding 4 copies, so I'll end up with 5 copies of my integral on this side. And then the rest I just leave the same. So that stays and that stays. So e to the x sine 2e to the 2x cosine. Almost done. I wanted, the original question was to find this integral. I don't quite have that. I have 5 copies of it. So if I want, I can just divide by 5. And I would get the integral that I started with, hooray, integral of e to the x cosine, is all this stuff here, e to the 2x sine plus e to the 2x cosine divided by 5. And now I guess we can add on a plus c. So
That was a long one.
it is. It is a long one. It's one of the longer ones, for sure. And trying to keep track of all the minuses and these 2's and, you know, what happens if instead of this being cosine x, it was cosine 3x? Now, then we'd be introducing not only multiples of 2, but multiples of a third. And so then you have to follow all those 2's and thirds all the way through. And you're not going to get 5 anymore. I don't know, you're going to get something else. And I think there is a general pattern for this. Like, instead of putting a 2 and a 1, if I put like an A and a B, you could actually derive this all out into a nice formula that only had A's and B's in it. And then you can just do a general formula. But Hartman didn't put that in the book. So, darn it, can't just use it. We have to work this all out. Unfortunately. So yeah, these do take time, for sure.
Thank you, sir.
Yep.
What about number 27?
27?
Yes, sir.
All right. What are you trying to do? Like find all the yucky ones, I think here. So, right, this is supposed to be integration by parts, which means you're supposed to have 2 functions. And it looks like I only have 1. You know, there it is. So when we did the natural log 1 in class, we wanted to write it as 1 function, which I already have, and then I multiplied by 1, so that at least I have 2 functions. If I don't have 2 functions, then I can't use integration by parts. So sneakiness, it says I can always multiply by 1, and then that will end up being helpful when I pick u, when I pick v prime. And so you gotta figure out which one of these is which, and turns out that u in our Lie thing, you could use that. Logarithms always go first for u, so that's over here. Natural log. I'm not saying it's going to be pretty because it's not. But I put the 1 for v prime, and I put this for the other part. Okay, then if you can get to that stage, so it's do this trig, figure out what u is. I still got to work through all the parts. So v, if I was in class, I would tell people, okay, I'll take v, and you get u prime. But I can't really do that so well. So v is x, because I just integrated it. What's u prime? So I have to actually use a chain rule on this, because it's squared. So that becomes 2 ln x plus 1, and then I got to multiply that by 1 over x plus 1. Oh, that's terrible. That's no good. But anyway, let me just see how long this condenses out to. Yeah, it's okay. It's kind of ugly. All right, so let's put this together. That means that this integral will be u times v, and I've got an x and I've got log, and typically, I don't know why I put that there. Equals u times v. So u times v will be x times the natural log of x plus 1 squared. And then what about the rest? Well, it's pretty bad. I've got x, and I've got 2 and I've got log, and I've got 1 over x. So we're going to put all those pieces in. I've got 2, and any multiples I kind of usually want to put outside. I've got x, I've got x plus 1, and I've got natural log of x plus 1. Like that. All right, that looks great. How do I do that? Well, it looks easy. It looks a little, well, I don't know if it looks easier or not. I mean, this is a square on a log, and that's not good. So we got rid of the square, but when we got rid of the square, we also introduced this junk right here. So I don't know. Hard to tell if that actually looks easier. It's true. The formula does work, but does that mean we can actually do this integral or not? I don't know. We'll have to see here. So, I'm trying to think of the best way to do this. I don't think you're going to like it so well, but I'm a math teacher. That's my job. If I divide, you're like, please don't do this. This is long division right here. I don't know if there's an easier way to do this, but I want to actually divide x plus 1 into x. So now we're going maybe way back. Maybe you've already purged these neurons from your brain. But if you divide, this goes into this one time. You multiply these two things together, and then you subtract. So long division. I subtract the x's off, I subtract the 1 off, and I'm left with the remainder of this. So what this means is that x over x plus 1 can be written as 1 with the remainder of 1 over x plus 1. Like that. And I'm going to substitute that in, and you're like, that's going to make it even worse. Well, almost. So let's see. I have the first part. And then the second part, I'm going to put this division in. So I have the integral 1 minus 1 over x plus 1, natural log x plus 1. Like that. Okay, why would I do that? Well, let's see. Keep going. I want to distribute this out into 2 integrals. So I distribute this out. One of the integrals will be 1 times this mass. And the other integral will be 1 over x plus 1 on the bottom, natural log of x plus 1. Yeah. So I distributed that out. There we go. So how do I do these? So now I've broken my first problem into the integration by parts. I got down to this. It didn't look easier. I had to do long division to get to here. I broke it into 2 integrals, and now I'm going to do each of those separately and plug the answer in for each one. So I have to do this integral, and I have to do this integral separately from each other. So here we go. I'm going to have to recopy this on the next page. So continue. Continue. Integral natural log of x plus 1 squared. I have, go back for a second. Yep. X natural log of x plus x squared minus 2 times the integral of natural log of x plus 1. And then if I distribute that minus 2, I don't know if I want to do that or not. Minus 2 will become plus. Plus 2 times the integral of 1 over x plus 1 natural log of x plus So still have that integral and that integral to finish things off. So I'm going to do this second one first, and we'll call this one 1 and this one 2. So the answer to 2, I just do u equals x plus 1. No, actually I've emptied that. Even easier. So I do u equals the natural log of x plus 1. Because how do you do u substitutions? You look for one function where the derivative is the other function. And that's exactly what I have here. Derivative of log is 1 over. If I do this, then du is 1 over x plus 1. And that last integral, it becomes very easy. It just becomes the integral of u du. So u is the natural log, and the 1 over x plus 1 dx becomes the du. So I'll get 1/2 u squared, and then I'll replace, and I'll get 1/2 of the natural log of x plus 1 squared. Okay. So that's that integral there. I'm gonna have to double it when I put it back in, but that's that one. This one right here also is a substitution, except this one is just x plus 1. So you're like, does that help at all? Well, we'll find out. Du is the derivative of x, which is 1 dx. So that integral becomes the natural log of u. That one we did do before. It is in the table. So if I went back to the table, it's number 7 right there. And we did do it before. So the integral of a natural log is x natural log x minus x. So I'm just going to use that. It's not x, it's u at this stage. So I get from the table and from class before, this is u natural log u minus u. And then replace. So this x plus 1 comes back in. It'll be x plus 1, natural log of x plus 1, minus x plus 1. So if you haven't fallen asleep yet, overall, the integral of my problem, or my original problem, is going to have 3 parts to it. The first part I got from the original integration by parts, and I think the square is not on all of it, just on the second part. So that should have gone there. All right. So only the square on that. So the square is only on that. And then I will have minus 2 times the answer for integral 1. So I have minus 2 times this integral x plus 1, natural log of x plus 1, minus x plus 1. So all I do is just take this, it gets a minus 2 factor on it. And then finally, the last one has a 2 factor on it. So, but my answer has a half in it. So this half, when you plug this in on this 2, they get eliminated out, and you just get the natural log of x plus 1 squared. Let's see. Anyway. You like that one?
Never, sir. I will never see it again.
Yes, that's a good thing to want. I think in the back of the book it does this. It says that this and this, look, they're the same. This one's multiplied by x, and this one's multiplied by 1. So if I combine those two and factor out x plus 1, I'll get the natural log of x plus 1 squared. And then if you distribute this 2, you'll have minus 2x plus 1 natural log of x plus 1. And if I distribute the 2 on this one, it's 2 times x plus 1. And I think that's probably the form that you see in the back. So it's our answer just reorganized a little bit to look like theirs, and then plus c on it. Hey, it's your fault, man. You picked out the hard ones.
Anyone that gave me trouble, sir. I scratch my head every time I see them.
That's all right.
Are a lot of the problems in the homework this complicated? Because I had a hard time with like a lot of them, but I don't know if it was just me or if they're all like this.
Those are probably two of the harder ones. I won't say that any of the other ones are that much shorter. I think if you look up through like 5 through 11, those aren't too bad. 12 through 15 are like the one we did. 16 is pretty easy. The inverse trig function, we didn't actually practice it enough. We should have. I hope you don't have too many of those because I don't take them. And then like 21 through 27 are log functions, and after that you start conducting twigs. These are definitely not easy.
Sir, can I see something on the previous page?
Yeah. On this page?
Yeah, I got it, sir.
Okay. So, I mean, Virginia, if you want to go over some more, we can. They really do take a while. It's a lot of algebra, figuring out U and V carefully. Maybe some of these little tricks of introducing one here or there. Not easy.
Okay. I think I just need to go back and read the chapter in the book and then try some of these again. Are we going to spend time on this in class tomorrow too? Like if other people have questions, or is this it?
Well, I mean, I'd rather you get them right than worry about an artificial deadline. So if you want to hold off on some of these, that's fine. If you want to email me, maybe I can send you some hints. But I'd rather you get them right.
Okay. I'll read the book and then try them again. Thank you.
What about number 33?
Right, you look at this and now you're like, now there's 3 functions in there. What are you doing? There should only be 2.
That's exactly what I thought.
Okay, so I grouped them. How about that? So I grouped them into 2 functions, and I'm going to let U be X, and V prime is both of these things together. It might make more sense based on what we did today, because if you do this, put both of these with this, then U prime is 1, hooray. V is the integral of this, which is actually secant. So this actually is not too bad. I get X secant minus the integral of these 2, the bottom 2 multiplied together, equals secant. Okay. So that's the first difficult step, is realizing that you need a group here. And then the second step is to say, well, crap, is that any easier? And the answer is yes, because we actually derived it, but you can also look back in the table, which one was that, number 13, realize that I could just use the fact that the integral of secant is that one right there. So using the table, the first one is what we got from ours. The second one from the table is this is the natural log of secant plus tangent.
Natural log of secant X plus tangent X.
Right, that's the integral of just secant by itself is this really ugly answer. But we derived it today. It's in the table. So use the table or remember it. I mean, it's a weird one.
The table that's in the lesson, or is it the table that's like behind of the book?
This is in the appendix. It's like the A17. It's the 17th page of the appendix. In the table, in the section, Yeah, I don't know if he consolidated that all down. No, I don't even think it's in, maybe it's in 6.1. It's, yeah, one of those. It is in table on page 271 in the book, but again, it's one of the integral ones, so it's probably best to just hop to this appendix page where everything is all in one place. Although that could be overwhelming too. I don't know. You got a lot of stuff. And how many integrals are in here? 33 are in the
Yeah.
table. And that,
Wow.
that book I was telling you about literally is over 1,000 pages that look like this. It's scary. And that's just for the ones we can do. That's scratching the surface. Most of the ones you can't do at all, and you just have to say, I don't know the answer. So it has to be very precise and balanced to make everything work out. But even then, it looks bad.
I think that was all my questions, sir.
Okay. All right. Well, enjoy the afternoon games.
Thank you, sir. Have a good day.
Thank you, sir.
Jordan, you there?